want to kind of break it out a little bit into like the technical components of it, and then we'll get into a lot more detail on each one of those. So as we evolve the architecture itself, as I said in the beginning, we started with this traditional data warehouse, single big box from a single vendor, let's say Oracle. It did everything for you. The query engine, the planning, the metadata, transactions, compute and storage, all that stuff was great in one place. It was nice, but it got expensive. It was very hard to scale. And it started to break when you were doing a lot of diverse use cases like queries and transformations and ad hoc analytics. It started to kind of fall apart. So when we transitioned that warehouse idea or concept into the cloud, vendors kind of rethought the idea and said, well, what do we separate storage? Because the biggest concern is I got so much data that I want to do something with. The cost of storing that data and the cost was basically increasing the cost of the compute layer. So if we separate them, now the user can pay separately for storage, but maybe not have to scale up the compute layer. So that saves them money that way. So the compute layer still maintain a lot of the logic, like the query engine, the SQL processing, metadata, transactions, all that stuff. We simply move the data to an object store. Now, we moved into the data lake. We sort of said, hey, we saved some money. We separate storage and compute. What else can we do? What's another bottleneck that we can abstract? And we extracted the metadata layer out of the warehouse component. And by doing that, now we have the ability to distribute that metadata across multiple environments. So if I want Presto and Trino and Spark and let's say Redshift to be able to understand which data sets are available and where to find them, I need a decoupled catalog that's accessible by those tools. So Hive Metastore came around, AWS Glue Data Catalog came around, and that gave you an external system of record that can tell any query engine where to find data and what's the schema of that data. And that's what the data lake gave us, data lake of 2-3 years ago. Fast forward to the Lakehouse, we broke that out even further. So one of the big aspects of a warehouse is the ability to use transactions in isolation to be able to commit changes into the lake. With a traditional data lake, that component was baked into the engine. So if the engine supported updating data in the object store, it would work. But if it didn't support that, then it wouldn't work, right? So if you wanted to do CDC, change data capture from a database into the lake, that engine that moves the data, like Spark, had to implement the updates and delete mechanisms. Often they did not. So you had to write your own code. And this was really hard to do. So in the Lakehouse architecture, we sort of evolved that piece and we extracted that transaction layer into its own separate layer with its own separate sort of APIs and abstraction that each tool that is able to integrate with it can sort of take that off the shelf and say, okay, cool, that's how I'm going to implement these transactions. So it's a consistent behavior, consistent concurrency model across the board. Now, there's another piece to this, I call it table services, that allows you to actually maintain the data in S3. We said in the beginning that in the data lakes, it was really hard to compact the data, to merge it. It was hard to optimize it. So these table services, again, are API abstractions that are layered on top of best practices. What is the best size for an object to get the best performance, right? So I want it to be a 256 megabyte of size. Okay, cool. My table services can manage that. It's not something that I as an engineer or I as a user need to know. So we'll talk about what that means.